So using one example to illustrate how this the network learns. So we have, as I said earlier, I modeled that threshold as another weight. So we have x0 all being ones. That's our artificial thing in order to bring this weight into the picture. So we have our function here is this, the sign function. We do a weighted sum of all those input and decide the sign for this value. And our learning rate, lambda, is 0.1. Our weight updating function is given here. So initially we have a random set of weight. We set it to be 0. And then we read in the first examples. The first example is 1100, and our label is -1. So with 1100 input into this network, we need to compute this output function f. So we put the value here. Weight are all zeros, right? Therefore, our y is going to be 0. Then our function outcome, what was our sign function? If it's greater or equal to 0, then the sign is 1, okay? So then in this case, our prediction is 1. So this prediction is different from this prediction. Therefore, we need to update our weight. So the weight is updated this way. Initial weight here is 0 here. So we add lambda 0.1, and our y was -1 minus our prediction is -1. Then we time this x1, that was the original one, and this gives us a new weight of -0.2. So we put it here. And we do the same for the second. For the second weight here. So it was initially 0 learning curve, lambda learning rate. And then so all those are going to be the same for every node that we work on, because the difference, the error was the same. But the initial input is different. So we have 100, so here is 100. So this gives us a new round of weights, and we put this new weights here. And then we read in another example, and using this new weight to compute the f, the function. And we compare this function and find the difference, and we go through the same thing again to update this weight. We will go through this for all the training examples we have. We're going to do that randomly. So we pick a random example, update, pick another random example, update, pick another random example, update, until we completely run through all the training example. That completed IPOC. And we do that multiple epochs many times. So you can see that the training process is computationally heavy. And this is our result of the IPOC. So after the first, at the initial thing, we have all zeros. After the first IPOC completed, we have this set of weights. And we continue and do this until some termination function is completed. So to summarize, the learning process is the process of reading an input example, go through the network. This is called feed forward. So here we only have one node, so still it feeds forward to this output function. If you have hidden layers, the values and the weights help you to fit their value to the next layer. And those nodes will output additional, send their output along the way to the next layer until the output layer is reached. And then we compare the system's output function with the truth and find the error and then adjust the weight. When here we only have one layer of weight, when you have multiple layers, the arrows are propagated back. It's called back propagation. So every weight in this network is adjusted for the next example. Okay, question. In this perceptual example, we can see our Wx is a linear combination of the input variables. So that our decision boundary is linear. In general, artificial neural network does not want a linear decision boundary. That's why different activation functions are used. So if you use a linear function, linear function like this for your activation function, your entire network will be only useful for linear separable data. If you use those curvy things, and those things, really, you will have a nonlinear, you can learn approximate any nonlinear and linear functions. And there are various types of neural network that has been used. Single layer network perception is one example, and versus multi-layer network with m number of hidden layers. Networks, a lot of them are feed-forward, like what we just demonstrated, but some are recurrent network, which means that the information can actually feed back from a later layer to a previous layer. For text processing, the long short-term memory machine is an example. I mentioned before, the nodes in a neural network does not have to be fully connected, but a lot of times they are. So learning the network, I think we actually went through this already. Feed forward is to get to the output and then find the difference and then back propagate the arrow. And we go through this earlier, but the idea of back propagate arrows is a way of minimize. We want to find, we want to minimize the arrow in the direction that would reduce the arrow the fastest. So again, we have a cost function that's non-convex. So therefore, we will do gradient descent to find the global minimum, find the direction where we want to descend to reduce the arrow. This is a visual. I want to show this very, very quickly. It won't take long. For a neural network, repeating what we just said, it's just a different way of looking at it. So we're going to have initial random weights on all the edges. And then we randomly select one training example. We feed forward and find the output. We compare the output to the real value that gave us the arrow. And we see there's an arrow. We propagate the arrow back onto each layer of the network, and resulting every layer's weight being adjusted in the direction that would reduce the overall arrow of the network. So that's the curly thing, the learning curve and the gradient descent technique. So we update the weight, we present another random example. We find the difference, and we again go back and adjust the weight until we have completed a certain number of epoch, or our performance of the network has reached certain things. it's a very, very long process to train a network. Looking from another perspective, initially see your data points are distributed this way and you have this random set of the weight. Your current network with the initial random set of weight are going to create a decision boundary like this, maybe. That all the things here are going to be considered predicted as yellow, and all the things above predicted as blue. Then we keep on updating the weights, and then the performance is going to adjust the decision boundary changes. We do it many, many times. If you don't stop it, it will definitely overfit your data and make a perfect prediction. There is also a live demonstration that you could actually play on your spare time. That you can actually generate a different part of the different data sets and see how configure neural network and see how it learns over time. And the concepts in the live demo that I have not covered here in this lecture is batch and regularization. They're pretty basic and important concepts, so I thought I should cover, even though our example did not touch upon those. Earlier we said every one training example going to result in an update of the network's weight, all the weights within this network. But you don't have to do that. So batch is a concept, the number of the training examples processed before you update the weight. We did batch size equals 1, so every one training example processed, we update the weight. But you could actually have other batch sizes. For example, I process every 10 examples, then I update the weight. You could also, in other extreme, I could process the entire training example, then I update the weight. So one epoch actually update the weight once. So there's different way of training. Which way is better? Really, I can't answer that question. It's totally depend on your application. You have to try different ways. Regularization is a technique because artificial neural network can approximate any function. It's as powerful, probably more powerful than decision trees. When we study decision tree, overfitting is a big concern. Similarly here, overfitting is a big concern. So the loss function that we, by the way, loss function is also called objective function. They're all synonyms. What this function does, you can see this is the true result. This is our output, and we found the difference. We want to minimize this, right? But this is the original loss function that we want to minimize. But in order to prevent the network from overfitting, we would add another term. So this is called regularization. There's two options. One is called L1 regularization. So this is just basically the absolute value of the weights. So beta here represents all the weights in the network. L2 is square of the weights. So between these two, so what you can see, the system is trying to penalize because we want to minimize the whole thing. So the system is going to penalize the weight that's too large. The system wants weight to be small and distributed. They don't want the weight that's overly big that overfits certain phenomena. So that's the use of the regularization. I think almost all network use regularization. I think L2 is used more often than L1, and L1 has a special feature that it can, depending on your setup of this lambda, this lambda is actually control this the effect or the extent of regularization. It's not the learning rate lambda. So this lambda, depending on this L1 tends to drive certain weights to 0. This, in effect, is similar to that you certainly disabled some features in the network, because when the arc has the weight of 0, and then that information will not be able to pass, the output from that node will not be able to pass to the following layers. So this has an effect of feature reduction. Some applications find feature reduction useful because the feature was really, really messy. L1 regularization help the system to select features. But majority of the applications seems to me that L2 is used more often.